Hello, everybody. Welcome to the lecture on plate tectonics. This happens to be my favorite field, what I studied in grad school, tectonics and structural geology, which is the deformation of crustal rocks due to plate tectonic forces. And here we're going to cover just the basics. Um, and if you ever wondered who runs the world, you might think it's Elon Musk or the Illuminati, but you'd be wrong. It's plate tectonics. And plate tectonics are responsible for just about all geologic features that we see um, in the bedrock, the deep crustal rocks. But also, plate tectonics drives the mechanisms that form just about everything on the planet. So therefore, it's a unifying theory, which I'll get into. Um, but because of plate tectonics, we have glaciation, we have runaway greenhouse effects in geologic time, because as these plates move around, uh, whether they be continental or oceanic, they change the landscape, they change how close different pieces of continent are, how close they are to the equator, or how close they are to the poles. And this drives weather patterns, drives climate, drives erosion, drives the deposition of sediment, drives the composition of the atmosphere through volcanism and all sorts of things. And so it really is the driving force on the planet. And so it's sort of foundational to all geology. So one question I'm going to pose in lab on Thursday is, what do you know about plate tectonics as a class? And we're going to sort of discuss some of the things you might know, things you've heard, some misconceptions. We'll talk a little bit about previous theories. But anyway, also on Thursday in lab, we're going to be looking. We're going to do a short activity that's not really part of the labs that I've posted for you to print, but we'll do an activity as a class with some in-person tactile sort of materials, posters, and things like this. And in groups, you'll be looking at some of the features that we see on the planet around plate boundaries mostly, and how this will kind of illustrate how geologists have been able to piece together plate tectonics over time based on the features that we see, and more recently with satellite data, GPS data, things like that. So let's begin by talking a little bit about the Earth's internal structure. So on the right there, we have a diagram of the Earth's major components, which I discussed, I think, a little bit in the intro lecture. And here we have some distances or some thicknesses. So at the very inner part of the planet, the very center of the planet, we have the inner core, which is about 1,200 kilometers thick. And it's made of solid iron and nickel because they are the most dense. And so in a molten planet, of which we were one, about 4.5 billion years ago, that stuff would have preferentially sunk to the center where the gravity is the highest. And so the most dense material migrated there. We have the outer core, which is about 2,300 kilometers. It's mostly molten iron and nickel, extremely dense, but not solid. So the key here is that it's molten, and that's this outer core here, if you can see my laser pointer. Then we have the mantle, which is about 2,900 kilometers thick. It sits around the inner and outer core, and upon that mantle, which is a rocky shell, partially molten and convecting in places. Remember I said like a lava lamp, sort of deforming kind of plastically. It's not quite a liquid, it's not quite a solid. So we say it's partially molten, but it's just, it's moving very, very slowly. And then on top of that, we have a crust, which if you think of the Earth like an egg, the crust is the thickness of an eggshell. I mean, it's very thin compared to the rest of the planet. It's only about 5 to 70 kilometers thick, 70 kilometers at the continents, and as low as 5 kilometers and the oceanic plates or oceanic crust. And you'll remember that plate tectonics is a unifying theory. That is, it is a theory that brings together a lot of disparate or separate parts of geologic study and helps to bring them all together into one cohesive, sort of unified study of geology. And plate tectonics helps us to explain why continents behave the way they do, why the oceans behave the way they do, why mountains behave the way they do, why sediments behave the way they do, rivers, the distribution of different fossil types, and the evolution of life on the planet. Plate tectonics is a theory that brings all that together. So what is the theory of plate tectonics? Well, basically the outer layer of the Earth, or the crust, and from here on in I'll use another word called lithosphere. So the lithosphere and the crust are more or less the same thing. Litho just means rock, so the rocky part of the planet, which is the outer crust, so we call it a lithosphere. Basically it's made up of broken up or separate rigid plates. Rigid meaning that they're solid, right? And they can be brittle, they can break, and at depth they can be deformed. So the idea is that plates move on the Earth's surface. They pull apart, that is, move away from each other. Like here we're seeing that. At this boundary here, these two are moving apart, and here they're moving apart, and up here they're moving apart. These four plates are, their boundary here is in the middle of the Atlantic Ocean. Sometimes they collide. So here you'll see this arrow where this Nazca plate is colliding into the South American plate. So the arrow is moving in the direction of the plate that it's colliding into. And then they also slide past each other. So it looks like there aren't any of those boundaries in this photo, but we'll get to that, don't worry. And like I said, a unifying theory or paradigm explains many different geological features, processes, and phenomena. So what about the plates themselves? So the rigid outer layer of the Earth, these are the tectonic plates. This is where they live. The crust and part of the upper mantle make up the lithosphere, or plates. So the crust here would be kind of just this continental crust here and this oceanic crust here. So these are proper the crust, right? And then also you have the lithosphere, which is kind of the very top part of the upper mantle, okay? And I might have mentioned this in the last lecture, but the mantle is it's separated by density and usually by temperature. So different parts of the mantle will be more dense or less dense or hotter or colder, depending. And at the very upper portion of the mantle, where the crust sits, we have this thing called the plastic asthenosphere. And now, if you've ever melted plastic before, you know that it flows very slowly. Imagine like if you had cold honey, right? How slow that would move. The asthenosphere is very similar to that, and it's the part of the Earth that the crust sits on top of, allowing these plates to slide over the top of it. Altogether, this makes up about 70 to 150 kilometers of the outer surface of the Earth. It's made of continental, like I said here, and oceanic crust, shown here. One thing you'll notice about oceanic crust is it's generally thinner, and it's more dense, so it sits lower. And you say, wait, no, it's not sitting lower than this continental crust. And the way I want you to think about that is this is more dense, but it's thinner. This is less dense, but it's thicker. So imagine if you had a tennis ball and you dropped it in a pool, and then you had a volleyball and you dropped that into a pool. The volleyball might be less dense overall than the tennis ball, but it's bigger. And so it's going to sit deeper to find that equilibrium as it's sort of floating in the water. Whereas the tennis ball might be heavier. You can tell I don't play tennis or volleyball because This analogy might not make sense, but imagine a tennis ball that's denser. It's just smaller, right? So it's not going to sink as deep down into the pool. And that's what oceanic crust does. So continental oceanic crust, they move on the asthenosphere, like I said. So here is a good slide, I think, to return back to. I won't go too in depth now, but here's a cross section of the Earth. Imagine if you cut the Earth in half and you were looking at it from the side, the types of things that you would see. And this image does a really good job of illustrating how these plate boundaries here sort of interact with one another. So here's that divergent boundary. So where they're spreading apart, we call that a divergent boundary. And pay close attention here to kind of what's happening with this magma rising up. We're going to talk more about what's happening there. Then we have the part where they're sliding past each other. We call that a transform boundary. And the most famous example of this would be the San Andreas Fault in western United States. So think about where you've heard of that before and what kinds of things happen at transform boundaries. And then when you have convergent boundaries, or boundaries that where the two plates are moving towards one another, you have something like this where it's two continents moving together. And I want you to kind of pay attention to what's going on down here and up here. Mostly mountains are being formed and there's no subduction. Well, what's subduction? Well, subduction is what's happening here when an oceanic plate is moving against a continental plate. The more dense oceanic plate is going to preferentially sink below the continental plate. Now you'll say, well, wait a minute, that's not continent right there. Well, no, that's still continental crust. It's just lower and on that portion, so it is somewhat covered by ocean, but it's still continental crust. So let's talk about the scale of tectonic plates, so size. So if we were comparing a human to the oceanic lithosphere, and then comparing a human to the continental lithosphere, a human would be roughly the size of an ant. There's a human and an ant, obviously not to scale. The oceanic lithosphere would be about, if you were an ant, the oceanic lithosphere would be about as tall as the Varnum building, the tall blue building in downtown GR there on the Grand River. And the continental lithosphere, if you were an ant, is about the size of the Empire State Building. So I thought that this will give you a sense of just kind of how big these things are and why it's so difficult for us to drill to the center of the Earth, as they say, even though the Chinese are attempting to do it now. Think about which crust they would be drilling through if they were trying to get to the mantle. Would they be drilling through this oceanic lithosphere or continental lithosphere? So the surface of the Earth is broken up into 7 major plates. The Eurasian plate, the Pacific plate, the North and South American plate, the African plate, the Indian plate, and the Antarctic plate. Those are the 7 major ones. And then we also have smaller plates we call microblocks or microcontinents. And that we have the Juan de Fuca plate here, which is causing all that trouble up in the western part of the United States. We got the Cocos plate, which is interacting mostly with the South American plate, or Cocos plate, and then the Nazca plate also interacting with South America. And here we see that, the kind of different boundaries similar to that cross section. So here we've got divergent boundaries, here we've got a convergent boundary, and here we've got a transform boundary. We also have transform boundaries up here and in a few other places. And plates, remember, they move relative to each other. So if we were at the center of the Earth and we were looking up, we would see all the plates kind of moving in maybe a similar direction. But if we're standing on the surface of the Earth, the plates are moving towards one another or away from one another or sliding past one another relative to each other. And I can explain that a little clearer in lab if you have any trouble kind of visualizing that. I'll make an attempt to draw something on the board or something to maybe help you out with that. So what's driving plate motion? Well, this was very controversial and was the reason why plate tectonics wasn't accepted as a theory until as late as the 1950s, even though people had proposed it before that, maybe even 100 years before that. And the main argument here was what drives plate motion. If these plates are moving, why are they moving relative to one another? Why are they moving in different directions relative to one another? If the rotation of the Earth was driving the plates, then they should all be moving in the same direction. And it just doesn't make sense that some would be colliding and some would be separating and some would be sliding. And then it was proposed that plate motion was driven by thermal convection in the asthenosphere. And remember I talked about in the first lecture, the wax in a lava lamp moving up and down and moving back and forth. Think about it like that, as those mantle convective currents move up as they're hot and they're moving away from the core, so they're cooling down. They're going to hit the crust and they're going to cause it to either split here. Otherwise, there might be currents moving down, and that's driving some of these denser oceanic lithospheric plates to subduct faster or slower. And then as those plates are interacting with the mantle, they're causing all kinds of things to happen on the surface, like volcanoes and trenches and ridges and mountains and all sorts of things. And these interactions, again, create the three types of boundaries: divergent, convergent, and transform. So let's talk about these three types of boundaries in some detail, starting with divergent plate margins or plate boundaries. This is where plates are torn apart, and those fractures fill with magma. And this produces new slivers of seafloor and therefore new crust. So notice here in this little zoomed in section here of the Mid-Atlantic Ridge, which is a divergent plate margin, we have plates moving away from each other and magma upwelling from the mantle to fill that space, that void space where the crust is moving apart. And what happens there is the lithosphere, thins considerably, right? Because these are splitting apart. And the magma naturally follows this like a bubble in a balloon, in a water balloon. The bubble is going to rise to the top, right? When it does that, it cools and it creates a little sliver of rock right at the boundary, on both sides of the boundary. And then as that continues to move away, it moves up and continues to create little slivers, and therefore it's creating new oceanic crust as these things move apart from each other. So this is younger oceanic crust because it just cooled from the magma chamber. And out here, this was once over here, but now it's been moved all the way out here, so it's much older, it's colder, and it's thicker. Mostly due to sediment deposition from oceanic sediments, but we'll get to that. This new crust, again, is thin and more buoyant, right, because it's warmer. So these boundaries tend to stay where they are in the crust just because of that buoyancy. That's the preferential place for this magma to want to travel to, because this is more buoyant and it's higher up and it's thinner, right? Like I said, the thickness and density of the oceanic lithosphere increases with age. This stuff is older than this stuff, and this stuff over here is older than this middle portion. And they're somewhat symmetrical in the fact that this part here and let's say this part here, equal distance from the divergent boundary, are about the same age and about the same thickness. Now notice the ridge down here is not just one single line. It's actually a little bit of divergence here. Then you move over a little bit and there's some divergence there. This is somewhat due to the way the magma chamber is behaving. This also has to do with just the composition of the rock, the strength of the rock, where it preferentially wants to split. And notice something here. These are rifts, right? So these rifts are offset from one another. And so what do we see happening right here? What kind of boundary would that be, just at this little space between these two rifts? I want you to think about that. And geologists often call these boundaries constructive boundaries because they're constructing or producing new crust. So divergent plate margins, if we were going to summarize, they move apart. The plates are moving apart. They create new crust at the spreading center. It's where the plates are the thinnest and the least dense. Their thickness increases and their density increases as the plate ages or moves away from the boundary. And they're long fissures, they have volcanism, and they have shallow earthquakes. So another type of plate margin is a convergent margin. Convergence is based on the word converge, that is move together or run into, and that's exactly what's happening here. There are three types of these, and the one you're seeing here is what we would call a destructive plate boundary because it has oceanic crust running into continental crust. Continental crust, remember, is more buoyant, so less dense, and it's thicker, so it wants to float. It does not want to go into the mantle, whereas the oceanic crust, which is thinner, more dense, maybe even colder, you can kind of think of it that way. And it's made of different rock types too, which we'll talk quite a bit about in this class. That boundary, at that boundary here, this trench, this oceanic crust is sinking down into the mantle below the continental crust. And what we see here is flash melting, and I'll talk about that a little bit later. Flash melting of the mantle, causing it to suddenly become hot and liquid, and it rises up and moves its way through the crust and the lithosphere and creates continental volcanic arcs. So volcanic arc is something I want you to put in your brain and seal it there, because volcanic arcs happen on continents and they happen in the ocean. And what they literally mean is just an arc of volcanoes. If you look at a map of the Western United States, Western North America, and Western South America, you'll see a whole ring of volcanoes, maybe about 10 to 100 kilometers in from the shore. And that is a result of all the subduction that's happening along the Western Americas, all the way from Alaska, all the way down to Chile. So, one thing to note here, this trench where the actual subduction is starting to happen, where it's starting to actually sink down, this oceanic below the continental, notice it's not the actual shore, right? Because this is still continental crust out here. Like I mentioned, this is what we call the continental shelf. It often has a lot of oceanic sediment here on its edge there. And that's interesting because a lot of times we see that stuff getting pulled down and subducting with this oceanic lithosphere, and sometimes the products of those sediments end up in this magma here as it erupts. So the three types of convergent boundaries are oceanic to continental, which I just showed you on the last slide. Oceanic to oceanic, that's where two oceanic plates run into each other, and one will be denser than the other, and thus it will subduct below the other. And that also produces that same melting. And here we get another kind of volcanic arc called an ocean volcanic arc, or an oceanic volcanic arc, sometimes called a volcanic island arc. Then we have continent to continent convergence, and this is where this was happening up top here for a long, long time. There was subduction of oceanic crust, but eventually on the other side of that ocean somewhere is another continent over here somewhere. And that's what we're seeing here. Eventually that continent runs into this continental crust, and we get what we call a suture zone, where two continental lithospheres are running into one another. And they create mountains. And in fact, they create the Himalayan mountains. And if you look below the Himalayan mountains, if you were able to do that, you would see the remnants of ancient subduction as the Indian plate's oceanic lithosphere was subducting under Asia's for a long, long time. And then eventually India came along and ran into it, and now nobody wants to subduct. They're both buoyant. They both want to stay floating. And so there's only one way to go, and that's up. All right, and that's mountain building. So these next few slides, I just want you to kind of commit to memory or sort of pay attention to the different features that we see at each one of these, because I've kind of gone over this drawing already. But before that, one thing I want to show you is, remember, you have this melting here, and as this stuff is melting and moving up through the lithosphere, it can sometimes pool at the bottom of the continent, in between the lithosphere and the continental crust. And then as it makes its way up into the continent, it can be active, an active magma body, where that stuff is continuing to rise up through the volcanic necks and erupt onto the surface as lava. Or it can stay stuck down here in the crust and slowly cool as something we call a pluton, where that stuff's never erupted up, but it was magma and it was slowly cooling. And when we get into our rocks and minerals identification portions of the class, there's different igneous rocks that come from here than igneous rocks that come from erupted magma. One thing I want to say quickly, magma is magma while it's in the earth or in the mantle. But once it erupts, that's when we call it lava. So those two terms are not interchangeable. Lava is erupted magma. Okay? So I want you to remember that. Now, the different features that we see at oceanic to continental convergence, or OC convergence, as I'll call it, is subduction, obviously, there. Shallow to deep earthquakes. There'll be earthquakes here as this is sliding past the continental crust. You get earthquakes there. But this subducting oceanic lithosphere is interacting with the asthenosphere, right, or the upper mantle. And it's also buckling and cracking relative to itself, and that's causing earthquakes too. So we see earthquakes all along this oceanic lithosphere going way, 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 way down, even past where the slide would show. A modern oceanic continental convergence, or OC convergence, can be found down here, like I said, in the southern portion of South America, or western portion, pardon me, of South America, where the Pacific plate all along here is subducting underneath the South American plate. And there's that volcanic mountain range that we see moving all the way up. And this is what those volcanoes look like. This is in Chile. And so this would be a typical continental volcanic arc volcano or mountain. And similarly, we see these in Oregon. We see these in Washington. They're in California. And British Columbia, as well as here in South America. Then we have oceanic to oceanic, or OO convergence. OO convergence, like I mentioned, still has that subduction of one more dense oceanic piece of lithosphere or crust moving under another. You get that same island or volcanic arc. Here it's a volcanic island arc instead of a continental volcanic arc. And the features we see here, again, are subduction, shallow to deep earthquakes, and that volcanic island arc, right? So we wouldn't, I mean, these are volcanoes. And this is, think like the Aleutian Islands in Alaska. To some extent, Japan is very much like this, although it's formed by a slightly different process, but there is subduction happening between two oceanic lithospheres. Hawaii, on the other hand, is not this. There is no subduction in the middle of the Pacific, but we'll get to that. Modern day oceanic convergence, or OO convergence, again, like I said, the Aleutian Islands. This is on the bottom of Alaska there, where the Pacific plate is subducting under this portion of the North American plate, producing these volcanic islands here. And that's what they look like. And they just look like an island made up entirely of a volcano or a number of volcanoes. And I've never been there. I'm sure it's pretty awesome. And for the third type of convergence, continental to continental, or CC convergence, we tend to see no subduction any longer. Now here, there's an oceanic plate that was once subducting, But now that the continent has come along that was attached to that oceanic plate, now this continent is slamming into another continent under which that oceanic plate was previously subducting. And here we get that mountain building, like I said. And this might be a little tricky because I'm saying here no subduction, but there is subduction in this picture. It's just no longer happening anymore. All right, this is stagnant now. These plates are now not really moving together very fast, where this plate's still moving down. Now these plates are kind of just pushing material up. We call that a suture zone right here, where the two plates are suturing together in a mountain belt, right? And it also says there's no volcanism here, and there's volcanism in this picture, but that volcanism is either left over from this subduction, and it's occurring very, very, very low in the root of the mountain belt. But on the surface, we would see no volcanism at all, okay? We do have earthquakes at CC convergent boundaries, and we often have high mountains, again, like the Himalaya. Although there have been ancient mountain belts the size of the Himalaya way earlier in Earth's history, billions of years ago, as a matter of fact, that would have been as big or rivaled the Himalaya, but they're very old and they've long since been eroded away or covered by ocean sediment and things like that. Modern CC convergent boundary, there they are, the Himalaya. Probably the most famous mountain range in the world and the highest. And this is directly due to the convergence of the Eurasian and Indian plates. And then our third type of plate boundary, aside from divergent and convergent, is transform. And this is where things are sliding past each other. Now, you'll say, but Eric, this is a divergent boundary, and this is a divergent boundary, because I was paying attention earlier. And you were, and that's true. But remember, right here, these two plates relative to one another, even though they're caused by divergent boundaries, relative to one another, they're sliding past each other here, okay? Once we get past that, they're moving in the same direction. And once we get on the outside of this divergent boundary, they're moving in the same direction. But in between, they're moving in opposite directions from one another. And in geology, on a map or a diagram, we denote that by these two arrows moving in opposite directions. Oftentimes, it's a half an arrow on either side. You'll see that there. It's sort of like half arrows. And these have no volcanic activity. There's volcanic activity at this divergent boundary. But here at this transform boundary, no volcanism on the surface at all. There's no reason for there to be. And this has strong, strong, strong earthquakes, okay? On the surface anyway, right? So this is the San Andreas Fault. And there it is, the San Andreas Fault, rather famous picture in the California desert, just south of San Francisco, I think, a little bit. So here, if you go into the actual slides that I post, I highly recommend clicking on this animation, and it kind of recaps the theory of plate tectonics and the different boundaries. So I'll let you do that on your own time. And so the activity that we're going to do on Thursday is going to show you sort of the most obvious evidence, I suppose, for plate tectonics, namely where there's mountains, where there's volcanism, where there's older and younger crust, things like that. But some additional evidence for plate tectonics is earthquake patterns, and one is the Benioff zone. So the Benioff zone is, remember I said in this slide here, oh, it's not going to let me go back when I'm recording, sorry. If you think back to the slide where I was talking about subduction and how that subducting oceanic crust is experiencing earthquakes all the way down into the mantle, we call that the Benioff zone. And then what that means is if you're standing at the plate, the actual plate boundary, and you're looking towards the continent that the crust is subducting under, If you're standing right at the boundary, the earthquakes are very shallow. Then if you move onto the continent, you'll go deeper and you'll see earthquakes. And if you move even more on the continent, you'll go even deeper than that to see the earthquakes, because you're looking at the earthquakes on the subducted oceanic crust as it's sinking down. So the further inland on the continent you go, the deeper that subducting oceanic plate is below you. We also have paleomagnetism. So this is a really interesting thing. We're going to have a lab about it. But the idea here is just the same way as a needle on a compass floats and points towards north, there are metallic minerals that cool in a divergent boundary where there's magma. And remember, that magma is cooling and becoming oceanic crust as the oceanic crust is diverging at that boundary. And what happens is there are the North and South Pole, magnetic poles on the Earth. Everyone should be somewhat familiar with that. The North Pole is magnetic north, the South Pole is magnetic south. And these minerals will preferentially, floating in the magma, point towards north because they're magnetic minerals. Now, then that crust then cools, and then that arrow pointing north is forever fixed in the rock and tells us what direction that rock was moving relative to north when it was forming. Okay, and I can go over this more in lab because it's kind of a weird concept, but it was the thing that got me. I was a biologist when I took this class the first time, and this exact bullet point made me a geologist. It's kind of weird. So one thing that happens, and we're not entirely sure why, but there's some good theories out there. North and south poles on the planet, about every 30 to 50,000 years, they flip. And suddenly magnetic north is on the south pole and magnetic south is on the north pole of the planet. And we see that reflected in the seafloor. That's all I'll say about that now, but we will have a whole lab about it where you'll be using those flips to try to figure out how old the crust is and how fast it's moving. We have direct measurements now with satellites, so global positioning or GPS, so we can get absolute plate motion. So we know where the plates are at all times. We're monitoring them. We have GPS stations that are communicating with satellites, and we can actually measure the movement of the plates now. So there's really no doubt anymore that plate tectonics is a real thing because we can measure it directly from space. We have deep sea drilling and sampling, so we can get the age of the seafloor based on sediment thickness. And that can tell us how fast the plates are moving apart based on the amount of sediment that's been able to build up over time, and some isotopic or chemical data basically from those sediments to tell us something about that. We have hotspot volcanism. Now this is where you have a mantle plume or a hotspot that is just a particularly hot part of the mantle. And the plate's sliding over the top of it, and as this plate is over the top of that point where the hot spot is, it's erupting. And then the plate moves away from that spot, and then that island is no longer erupting, and it just becomes a volcanic island that's dormant. And then a new island starts to form on the part of the crust that's over the hot spot. And so you'll get these island chains. Okay, and we have an activity about that too if it's hard to visualize now, so you'll know more about that. But that's what Hawaii is doing. It's hotspot volcanism. There's no plate boundary there. It's just a hot part of the mantle. And then we get exotic terrains, which is subduction and plate motion. And exotic terrains, I'll get into a little bit, but that's what the western United States is like. So from the coast of California all the way to the Rocky Mountains, all of that stuff was formed through what we call shallow or flat slab subduction. And we can see evidence of that in the United States. So here I've got some slides to illustrate those things I just mentioned. So earthquake patterns. So this is the Benioff zone here. So you'd be standing, like let's say on this island, and you'd measure earthquakes just below you. If you move towards the continent this way, they'd be deeper. If you moved over here, they'd be even deeper, like down here somewhere, something like that. And we also see the distribution of earthquakes on the surface in the same way. So here's the trench. So this portion on the right is subducting under this portion on the left. And we see shallow earthquakes here denoted in blue, and then intermediate ones denoted here in green, and then deeper ones denoted here in red. So if we think about it, the plate is probably subducting this way because the deepest stuff is to the northwest. And so again, as I was saying, the Earth's magnetic field is further evidence of plate tectonics, because remember, at those constructive boundaries or divergent boundaries, where magma is upwelling and continuing to create crust as it moves away from the boundary, we see a preferential sort of alignment of magnetic minerals. And that's because the Earth is a giant dipole magnet. Dipole just means two poles, so a north and a south pole. And they coincide with the geographic poles. But if you look at the image there, so the geographic North Pole is the actual axis upon which the Earth spins. So it's fixed relative to the Earth. It does wander a little bit. The whole Earth kind of tilts over geologic time. But then there's the magnetic North Pole and South Pole, which wander around. And this is probably because well, first off, the magnetic field is generated by the iron and nickel solid core being surrounded by the liquid nickel and iron core, outer core. And so as those two things interact with each other, it generates a magnetic field. And that's what we think anyway. So what this is illustrating here is the strength and orientation of the magnetic field, and how that varies. So if you look here at the north and south, you'll notice that the magnetic lines here are more concentrated on the poles, and then there are no lines really over here on the side. So the magnetic field is stronger at the north and the south, and much weaker as these lines move out this way along the equator, right? So that's why minerals preferentially, or any magnetic material, metals, they preferentially line up with those magnetic poles. Oh, and I would click into the slides again and look at these demos if you want to see some pretty cool illustrations of how these magnetic field lines are generated with a magnet and some iron shavings. And just to reiterate, paleomagnetism is one way that we can tell that there's plate tectonics or evidence of plate tectonics, because we see in the rock record iron-rich minerals record the orientation of the North and South Pole over time. And like I said, you know, it aligns to north when that rock, or the magma rather, is cooling into rock, just like I said, a compass needle floats on water. Similarly, these iron-rich minerals will float on the magma, and then when it cools, it locks those in place. And so over time, you'll see different orientations that show that there's wandering. But the way that this illustrates the presence of divergent boundaries is that the magnetic poles, like I said, will flip. And sometimes the North Pole, or the area where the magnetic lines are entering back into the Earth, flips to the south. And this happens about every, like I said, 30 or 50,000 years. And so as that divergent boundary is generating new crust, we see kind of a stripe, you know, maybe a few kilometers long, or more, maybe 10 to 50 kilometers long, where all the minerals are pointing north, and then that same stripe after that, where everything's pointing south, and then it's pointing north again, and then it's pointing south again, showing that the divergent boundary is creating crust over time. And more evidence for that polar wander can be seen in different plates. So there's an apparent wandering path for Eurasia here, and then we can correlate that to the apparent polar wander path for North America. And this is by looking at rocks in the crust in both plates as they're being generated by that spreading center in the middle of the Atlantic. And at the time that the Earth was sort of in a phase where all the continents were clumped together in something we call a supercontinent. You've probably all heard of Pangea. That's the youngest supercontinent. There were actually a number of them before that. We see the polar wander is the same, and we can match those up and figure out where those plates were at the time that crust was being generated. And that's one of the ways that we can reconstruct where continents were at different time periods, because we can just match up the alignment of those minerals in the rock. And that's, like I said, one of the ways that we can tell where things were, close to the equator, clumped together, spread apart, etc. And here's an illustration of what you might see in the field if you were out, geologist out in the field doing field work, and you were looking at the magnetic anomalies in the rock. And so they would look at different layers that are being created in magmas. This is a volcano, so not a divergent spreading center, but more just lava being erupted on the surface of a continent. But the same thing applies here, where there would be iron-rich minerals in that magma as it cooled. And we can see here that at 1.2 million years ago, we had a normal anomaly. That's where north, where north is north, like it is today. And then we go about 0.4 million years in, and we see that it's reversed. And when it's reversed, we call that a negative anomaly. And that's when the minerals are naturally pointing to the south. And then another 0.4 million years, they're pointing to the north again, and so on. So we would see that in cooled magma that became igneous rock that has those iron-rich minerals in it. So here is a beautiful illustration of those magnetic anomalies in a spreading center. So here's the mid-Atlantic ridge here, going down north-south. And geologists will often use really precise instrumentation. In this case, we would use something called a magnetometer. And you can either attach that to a boat and sail across the Atlantic, or, well, not sail, but, well, maybe. And then, or we could do it by plane, because we've gotten really good at creating very precision instrumentation that's super duper sensitive. And so we're able to fly over as well and map the magnetic anomalies recorded in the rock record on the seafloor. And so these stripes that you see here in yellow and red and purple are different magnetic anomalies, and we can see that there's sort of a pattern, almost symmetrical pattern. So on the east side of the rift, we have this red, and then on the east side of the rift, kind of at the same distance, we have that red. So that's showing that we had a positive anomaly, and then followed by this yellow, which would be a negative anomaly, and then positive anomaly. So these are the poles flipping back and forth. Also, one thing, so that illustrates, that there's spreading happening here. So evidence for plate tectonics. But also, remember from the previous slide, I was talking about how at spreading centers, because they're offset, and they're spreading at different rates along this spreading center, we also have transform or slip strike boundaries, where the plates are basically sliding past each other because of the different speeds of the spreading south of this line and north of this line here. And you can see that the magnetic anomalies come down and then they're cut or offset by that fault there. So that's evidence also of transform boundaries being associated with divergent boundaries. All right, so I'm sort of beating a dead horse here, but here's kind of a cartoon version of that. So here's a period of normal magnetism where they're spreading and all the minerals are aligned to the south here, or to the north, I should say. So maybe we're standing north and looking down, because that's normal magnetism. And then reverse magnetism, everything flips. And so this is these yellow and red stripes that we see. Oh, and be sure to look at some of these links. Anytime I have a link in here, always click on it and check it out. Pretty interesting. So as I mentioned, we also use GPS, Global Positioning System. Here's a GPS unit here, pictured. So satellites would be reading that, and they would just fix that in a spot and then take off and do your thing, come back a year later, check up that the machinery is still working and all that. This is often the way that we record plate tectonics is sometimes we'll have instruments on the ground that are recording certain things. And we often would leave and then come back once a year and gather the data. And so a lot of times these sorts of data collection methods take years and years and years. But with satellite imaging and like I say there, the SLR, the satellite laser ranging, or the very long baseline radio interferometry. I got through that. That's nice. We can get kind of more real-time data, and we can correlate those three things together to kind of paint a larger picture of the types of things that we want to observe when it comes to plate motion and the interaction at plate boundaries. And here's what that would look like if we were to map plate motion. So these arrows here are actually vectors. So if any of you have taken physics and some calculus, you'll know that a vector is a direction and a magnitude. So it shows two different bits of data there. The arrow points in the direction of plate movement, and then the length of the arrow indicates how fast the plate is moving. So here we can see, this area here to the east of Australia, kind of in the middle of the Pacific there, is spreading away from this the Nazca plate, and it's spreading much faster, right? Because these are big long vector arrows. It's spreading much faster than, let's say, in the Atlantic over here, where we have these kind of smaller arrows. And notice some of these shapes it's making. These plates aren't, I was telling a student yesterday, plates are never just going straight at each other, spreading straight away from each other, or sliding perfectly past each other. Plates are rotating, they're buckling under different forces, and so it's really kind of a mess. But this shows you that the plates generally in North America is moving to the west relative to the Pacific plate, but also it's kind of turning, right? It's kind of curving down like this. Same with the Eurasian plate. And then notice the African plate's just kind of going straight up. So there's a lot of variation here. So in nature, nothing is perfect, but what we like try to do, and the way I'm going to teach this class is I'm showing you sort of the models that we use. And I had a chemistry professor once that said, all models are wrong, some models are useful. So keep that in mind when we're thinking about natural processes. It's usually a lot messier than we like to admit. So also some more evidence for seafloor spreading is done through deep sea drilling and sampling, where we can tell the age of the seafloor based on the amount of ocean sediment that has been able to accumulate on the top of it over time. So as you can imagine, right at the spreading center, a lot of this rock is, geologically speaking, brand new. So maybe only a few thousand years old, maybe a million years old. And then as we move away from the spreading center out, we see the crust thickening as ocean sediment, and that would be shells from plankton, mud, sand, limestone, which is from the shells of plankton and other sea creatures. Like it's made out of calcium carbonate, which is calcite, which is the mineral that makes up limestone. We see that stuff accumulates thicker and thicker as we move away. That's in this kind of light tan on the top here. So notice none here and a bunch over here. So over time, the crust will thicken, and so it's much thicker closer to the continents of, let's say, North America and Europe, or South America and Africa, than it is in the center of the Atlantic, where the crust is younger and fairly new. One thing to mention here is that ocean basins, so oceanic crust, where there are spreading centers here, are the youngest of the crust on the planet. The oldest oceanic crust is only 180 million years old. So at these constructive boundaries, crust is being created, and then at subduction zones, at convergent boundaries, it's being destroyed. So it's constantly being recycled. As the continents move together and spread apart and shift, that's all being driven by the spreading and subduction in the ocean. And so the continents, remember I said to many of you yesterday, the continents never subduct. We have 3.7, 3.8 billion year old crust. So it sticks around forever, basically, because it's so buoyant. It's full of silica rich rocks like granites and rhyolites and things like that. And so it's less dense than the basaltic rock that we find in the ocean. So the basaltic rock is always going to subduct. So the continents kind of stay permanently on the Earth, but in different configurations, whereas oceanic crust is spreading and subducting and then closing up, and then the continents collide, and then they separate again, and so on. Further evidence for plate motion is hotspot volcanism. So hotspots are volcanic features that are not associated with a plate boundary. They are associated with plate motion, but not a plate boundary. Volcanic islands and seamounts increase in age in one direction. So I mentioned earlier Hawaii. So this is a cross section of what this looks like. So up here on the top, we've got plate direction this way. Here's the hot spot or mantle plume, right? It's a mantle plume in the mantle, but we call it a hot spot because we don't know if it's attached all the way through the mantle. These are sort of controversial because it's still unclear if there are even mantle plumes that originate from the core and rise all the way up, or if they're just little pools of magma at the bottom of the lithosphere. But either way, they erupt up through the crust. So there's no plate boundary here. It's just an area where the mantle is hotter for whatever reason. It rises up through the crust and it eventually erupts on the ocean floor as a volcano. As that continues over thousands, hundreds of thousands, millions of years, it builds up and builds up and builds up, and eventually it pops up out of the ocean, continuing to erupt and becomes a volcanic island. Now you'll notice the plate direction is this way. So imagine this is your crust and it's moving in this direction. If we reverse time back, this spot up here was at one time down here erupting as a volcanic island. Then it moves on and then it's no longer erupting. It's now a dormant volcanic island, and a new island forms behind it. And it's moving, 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 and it keeps producing these islands in sequence as the plate moves over the hotspot. And we can see here, and this will be in one of your labs later on, I think volcanism, or maybe it's tomorrow's lab. I'll have to check. But anyway, we can see that the plate was moving north for a long time, due north, and then at some point it started to move northwest here. So imagine this spot up here in the Emperor Seamount chain, the very northern part up there by Russia, was once here, and it was moving north like this. Okay, and then the plate changed direction and started moving this way, and that's why we see this moving like that. Now, a lot of students will make the mistake that the plate is moving the opposite direction. For whatever reason, a lot of people get turned around by this, but I want you to think about it as, yes, if you reverse time, we're moving in this direction, but the plate itself is moving in the direction of the oldest island, if that makes sense. So eventually the big island in Hawaii will move past the hot spot. It will no longer be erupting lava, and a new island will begin to form beneath the surface, and eventually, if the plate stays, a slower speed, it has time to accumulate enough material to pop up and become a volcanic island. So one thing I want you to note is the size of these islands illustrate a couple of things probably. One thing it illustrates is that the plate was at a slow enough pace that it was able to build up, whereas some of these smaller ones, maybe the plate was moving over the hotspot faster. And so there wasn't enough time to build enough material for it to even pop up out of the ocean necessarily. You'll notice these are submerged here. Anything where you see green on them, that's an island. Everything else is sort of underwater. Another thing to note is that as I mentioned before, nature is messy. And as geologists, we would love to think that these mantle plumes or hotspots are fixed and they're just in one spot all the time, but that's not the case. In lab, you're going to kind of be asked to consider this in one of the questions, and that is, if this plume is wandering around, so it's sort of moving around under the surface, how would that change the way we calculate the rate of plate motion? So be thinking about that, because that's something you're going to have to address in an upcoming lab. Another very famous hotspot, this time underneath a continent, namely our continent, is Yellowstone. There have been movies about this. People talk about it all the time, that Yellowstone's going to erupt. It's a super volcano. It's going to kill everyone and destroy the world. Rest assured, there's been some papers coming out recently that have been monitoring Yellowstone for decades, and they're happy to report that they think Yellowstone will probably erupt in smaller sequences. It is about ready to erupt. Geologically speaking, it hasn't erupted for about 50,000 to 100,000 years, I think. But so it is still technically an active volcano. However, it hasn't. It's probably not going to erupt all at once and black out the sky like the movies tell you. But it is a hotspot, and we do have evidence as we move across the continent that we see where it was once over the hotspot and now where it is now over the hotspot, showing that North America is migrating to the west, slightly southwest. And that's how we get all these beautiful hydrothermal features like Old Faithful. This is Morning Glory Pool, and this is the Grand Prismatic Pool. This is because there's magma in the crust underneath that hotspot. It's not erupting currently on the surface, but it's heating all the groundwater. And when it does that, we get these beautiful geothermal pools that you can see. And finally, we have exotic terrains. And these are distinct blocks of rock found on continents that are physically and chemically different from one another, meaning that they formed under different conditions and have different chemical compositions, so different types of rock. Silica-rich rock butt up against basalt or magnesium-rich rock, and we see these, and they're usually bounded by faults. What does that mean? Well, that means that at one point in time, let's take this image over here on the right. Up in the left here, we see Gondwana, which is an ancient continent, ancient supercontinent, matter of fact. And it's bounded or bordered, I should say, by this subduction zone. And so here, oceanic crust is subducting down underneath Gondwana. It's erupting basalt-rich magmas due to the subduction. And as that moves up through the continental crust, it starts to incorporate more of the continental materials that it's moving through by melting that crust a bit as it moves up through. And so when this eventually starts to erupt on the surface of the continent, it has a lot of the silica-rich, what we call felsic magmas. And so when that erupts, we get a lot of silica-rich lava, which is called a rhyolite. And so that volcano is erupting there. And due to this subduction, here we're getting the deposition of something called an accretionary wedge, forming what we call an accretionary prism. And this is ocean sediment that's being scraped off of the surface of the oceanic plate as it subducts. And so that stuff is being deposited here in the trench. Then we have subduction over here on the right, and that's oceanic to oceanic subduction, or oceanic to oceanic convergence. And that subduction is also erupting basaltic lavas, but that's just moving up through oceanic crust. And so that's producing a basaltic lava, which is a basalt that's magnesium rich. And so it's forming a basaltic island, and all of this subduction is moving in the direction of this subduction. So you can think of this whole package here moving to the left. And as that continues, this island is continuing to grow. We've got an accretionary wedge to the right of it. We've got this accretionary wedge to the left of that island. And then we've got Gondwana sitting over here doing its thing. As that subduction continues, eventually all three of these things are going to collide together, or four things, I should say, are colliding together. Once that happens, this slab continues to move down and possibly breaks off. This is still being studied. We don't know. There might be just hundreds of broken slabs sitting in the mantle, slowly melting and becoming mantle rock again, where they'll be recycled as igneous rocks again at some point when they erupt or cool at the surface. Anyway, I'm getting ahead of myself. That's for later. What happens is this continental margin here, this subduction zone, ceases to converge. It's done now, right? And so this volcanism ceases. And that stuff just cools into what we call a pluton under the surface, which would be a granite. And then there's no longer active volcanism on the volcano here. So this accretionary wedge is getting pushed by this stuff behind it. It heats up, it gets pressurized, and it metamorphoses that accretionary sediment, right? This ocean sediment here that was being scraped. More on that when we get to metamorphic rocks. Then we have these ocean sediments that were over here on the left of the island here. That stuff also gets metamorphosed, and that's called an ophiolite. We'll talk about that. And then here's our island arc here. It's also being metamorphosed because it's under pressure and it's being heated up by that pressure. And so it changes the composition of these rocks. And then we've got this accretionary wedge here at this zone where it's still subducting. So this is still actively erupting basaltic lavas. And so this whole thing here, each one of these little pieces inside this whole thing are chemically and physically distinct. Different levels of metamorphism, different geochemical signatures. And so this eventually becomes basically a continent, right? And well, in this case, it's actually adding on to a continent, Gondwana. But you could picture this happening with a bunch of island arcs as well. Imagine there's no continental crust over here. It's just a bunch of island arcs running into each other. And geologists believe that this is probably how continents formed in the early Earth. Once plate tectonics got going, and it's not really clear when that was, but once it got going, all these little islands arcs are just suturing onto each other, right? Suturing and suturing, and it just starts to form the very early cratons, we call them. They're sort of microcontinents or proto-continents. And then over time, this just keeps happening. Island arcs just keep suturing on to continents, suturing on to continents, and suturing on to continents, and it forms what we call exotic terrains. So a perfect example of this can be seen in the western United States. And these exotic terrains make up about 25% of the western edge of North America. And they're a really good example of an active continental margin, as we know there's subduction happening with the Pacific plate underneath the North American plate, because we still have active volcanism on the west coast. None of you, well, maybe some of you are old enough to remember Mount St. Helens. I was a little kid, but so there are still active volcanoes from that subduction. But what we see, if we look over here on the western part of the United States, notice most of the United States, this is a geologic map of the US, most of these are either large sort of igneous provinces or sections of rock that are volcanic or igneous in nature. Some are large accretions in the east, like all of this kind of sutured on at different times. But a lot of what you're seeing over here is actually ocean deposits, shallow sea deposits of sandstone, mudstone, and limestone. Because we'll talk during geologic time, I think at the end of the course, sea level has risen and fallen for a number of reasons, and a lot of the early continent has been inundated by shallow seawater, and then it's fallen, and then it's risen, and then it's fallen, and so a lot of this stuff over here is sedimentary rock. But if we look at the Rockies and west, you'll see that it's kind of a hodgepodge of all sorts of different rock types. Probably because this is younger than the rest of the continent, probably hasn't been inundated by seawater as many times. And so a lot of this is what we call heterogeneous. And that means made up of different things, okay? So you can see it's just a mess over here. If we zoom in to the southwest of California and Nevada, you'll see something very similar to what I showed you in the previous slide. Down here, we have some recent sediments. And then in white there, you'll see, where is that? There's some here and here. You get, that's the accretionary prism. So that was that ocean sediment that was being scraped onto the continent. Then you'll have in red here some displaced granitic rocks. So these would be continental crust volcanic eruptions. Or no, pardon me, no, not eruptions. This would be chunks of magma that were stuck in the crust and cooled slowly, making a granite. We'll talk about that more when we get to igneous rocks. Then you've got some oceanic crust, and then you've got some island arcs here. So this whole area has been sutured repeatedly from subduction, and it just slowly adds on and adds on. And so what's subducting now would have been that far right subduction that we saw on the previous slide. So it was another subduction zone coming in behind previous subduction zones that have ended. Okay. So to recap, aside from some of the things we'll talk about in lab tomorrow, as far as different features across the entire planet that sort of show where plate margins are and some of the geologic features that indicate that, we also have paleomagnetism, direct measurement through GPS, deep sea drilling and sampling showing the thickness of sediments, hotspot volcanism, and like I just mentioned, exotic terrains. Tomorrow we'll kind of look at earthquake patterns on the surface, but we also have the Benioff zone where we can measure earthquakes as they're subducting down into, as that oceanic crust is subducting down into the mantle, because that continues to have earthquakes as it's subducting. So we can do some deep seismology there and find those earthquakes. So that concludes the plate tectonics lecture. I just wanted to point out a couple videos that I think would be good for you to watch. So go ahead and click on those links and check those out. Also, go to the first online textbook mentioned in the, well, I think either one mentioned in the syllabus, and go through the plate tectonics chapter. Some of you have already read it. Bravo. But click on some of the animations, because once I figure out how to put animations in these lectures, I will. But until then, click on those in the book, because I want you to kind of see. Sometimes it's a lot easier when you just see animations of these processes, because it really helps to make sense out of them. And with that, I will see you guys tomorrow in lab. Sorry I'm posting this a little bit late today. Going forward, everything should be up on Sunday for the whole week. I'll see you guys tomorrow, and have a good day.